Hello, welcome to lecture video 59 in the lecture Advanced Mathematic Modeling. So we were looking at metabolic scaling, metabolic theory, and we want to know why the metabolic rate scales with the body mass to a certain exponent. And we looked at some naive and simple geometric theories where we obtained scaling with an exponent, for example, with body mass 2/3. Whereas the real exponent is 3/4, and I introduced you to the theory of West, Bryan, and Enquist that they said, the important surface is not the outer surface of an organism, which would lead to this scaling here, but in fact we need the effective surface of all membranes of the system, where we have a fractal supply network which has then a huge fractal dimension, and so basically we could, if this is a space filling fractal, we would get a fractal dimension of the surface equal to 3, and maybe this could lead to this exponent 3/4. But in order to see if this really holds, we need to work it through and calculate what would be the fractal dimension in such a metabolic in such a fractal supply network. And that's what we now want to do. And I have to say, when I do this, I restrict myself to the most simple version in this West, Brown, Enquist theory, where we just have a constant flow. There is more sophisticated variants where you have a pulsing heart, so meaning you have a flow which is cycling, which is pulsing, and this makes stuff more complicated. So there are variants of this. And what I do now is just the most simple of these theories, but this will be technically enough for us, I think. Okay, so let's have a look what we are doing here. So first we have a branching network. This means we have here our aorta, and we say, so that's k equals 0. And then we have the first branching. Now we have our first vessels. Here we have k equal to 1, and then we have a next branching, k equals 2, and so on, and we have until a big K. That's the number of branchings. So our fractal, so we have in total k branchings, and remember, these are the branchings of the blood vessels in the body. For example, the aorta, here's k equals 0, then we have k equal 1, k equal 2, k equal 3, and so on. And we say the whole thing stops after k, big K branchings. So small k is the number which gives us our branching number. K equals 0, we are in the aorta, and k equals big K, we are in the capillary. Yeah, and that's maybe to repeat maybe the fundamental idea. So we have a fractal, the self-similar fractal supply network, where we start with a very big vessel, and we have these branchings and go to smaller and smaller vessels. But this branching stops at the end member, so the branching and that's the capillary, so that's the cell size, and we cannot simply by physiology cannot branch any further. So the fractal goes always until this end member. So this means the mouse and the elephant have the same size of a capillary here, but they have a different number of branchings, and the aorta will be different. The elephant will have a bigger aorta, so the elephant will have more branchings and a bigger aorta, and the mouse will be a scaled version of the elephant with just a smaller number of branches. Okay, and every vessel has a certain geometry. Maybe we plot this here. Geometry of a vessel, and that's always simple cylinder. So here we have a radius RK. So the radius of our cylinder depends, of course, on our branching level. If we're deeper in the fractal system, our radiuses get smaller. It has a certain length, LK, and also the lengths are reduced when we go deeper in the system. So then we have here the area, pi r squared, and we have a flow UK, that's the blood flow through the vessel. So the vessels are cylinders which have a certain flow, a radius and a length. The next thing, we need to know how many branches do we have, and then we say we have at level K we have NK branchings, branches, how do you say it? Branches, maybe. So this means here, for example, N would be 3. We go from one vessel, this is splitting up in 3 more. Yeah. And then, so then how is our fractal system, the fractal geometry is described? By the information on the number of branches and K, and then we need scale factors. Okay, we'll introduce them directly. I should have done this before. Beta K and gamma K, and the scale factors just tell us how does the radius in one level of the branching is compared to the radius of the next. So meaning here, if we maybe here you can see it better, if we have the radius of the big vessel and compare it to the radius of the smaller vessel, so this ratio gives us better, and gamma gives us the length of the vessel at one level to the length of the vessel in the next level. So beta K is just the radius at the next level, K plus 1, divided by the radius in the level K, and gamma K gives us the ratio of the lengths. So this gives us the length of the vessel at level K plus 1 divided by the length of the vessel at level K. And if we know the branchings, the number of branches, we know how the radius is reduced, we know how the length is reduced, then we basically know the geometry of our system. And but this would be now, okay, so that's how the geometry is described. And it's not so important for the result to know the angle. We don't care about the angle, it doesn't matter. We just have the geometry that we know at every point how many branches are going out of this and what is the length and the radius of a typical vessel which is starting at this level in the branching. But this now, if we have k levels, we need 3k informations. That's quite a lot. And now we want to simplify everything, and then we say we have a perfect self-similar fractal. And then this means that the properties of the branching are the same on all scales here. So this means if we divide here into 3 branches from the transition from 0 to 1, then from 1 to 2 we should also divide in 3 branches, and so on. So meaning this nk, they're all the same. And then we also say that the ratio of the radiuses should be the same. So all beta k are the same, beta and all gamma k are all the same. So we just have these 3 numbers n, beta and gamma, which tells us the number of branches, the reduction in radius and the reduction in length at every level in our fractal. So this branching process has always the same properties, and that's what we said before. That's a self-similar thing, and we want to have a self-similar fractal, and that's very nice because now we have just these 3 numbers. Okay, so we spoke about the geometry, lengths and radiuses. We didn't speak yet about the flow. So let's look at the flow through the vessel. The blood flow through a vessel, and okay, we call this Q is the flow, and at K, and the blood flow should be proportional to the area, P RK squared. That's the area of the vessel, the cross section, multiplied by the velocity, or the UK would actually be not the flow, it would be the velocity of the blood going through the vessel. And then the flow is proportional to the area times the velocity. And now we can see, so now what is the total flow? Because okay, now we have described basically everything we need to know about our geometry, but now we have to put the pieces together, because what's happening at one branch is connected what's happening at the other branch, because we have mass conservation. So if we have a certain flow of blood going through the system, after the branching we need the same flow of blood, and after the next branching again. So now we can look what is the total flow. So that's the flow produced by the heart. That's Q at the 0th level of our fractal system. So the flow through the aorta. And this must be the same as the total flow at a deeper level in the branching. So at a deeper level in the branching, maybe, okay, we forgot something. Where should I do this? I forgot to say something. Maybe I can do this here. What's the total number of vessels? Total number of vessels. So, and we call this NK. That's the number of vessels in a certain depth in the fractal, and NK is n0 times n1 times n2 until times nk, yeah, because we have to multiply in every branching. We have n more product times n more vessels, so we have to multiply all of these numbers. And since we said this nk are all the same, so this is actually n to power of k. That's the total number of vessels. And why is this important? Because if we want to know the total flow in the aorta, it has a certain value, and if I want to know the total flow, let's say in the second level, then I need to know what's the flow through a single vessel multiplied by the total number of vessels at level 2. So this must be equal to the total number of vessels at a certain level in the systems times the flow through a single level at this branching depth. And okay, now we can plug this in here. So we have nk, and we have p r k squared uk, and this should be the same. So that would be the flow at a certain arbitrary branching in the system, and this must of course be the same as at the capillary level when we have big K here, big K, P, R, capital K squared U, K. And now you see this here is just a property of the capillary. That's totally independent of the mass, because we said what's happening at the end members, it's the same for all organisms. That's the same for the mouse and the elephant. So this needs to be independent of m. Of the mass. But now, well, we can say, or the mass, the size of the system, but we typically say the body mass. That's how our measure of the size. So that's m, the body mass. Did I introduce this already? Not yet. M, that's the body mass. And now our metabolic rate. B, yeah, that should be proportional to the flow for the aorta, because like we say, every metabolic activity in the body needs to be supplied by our fractal system. Yeah, so it needs to be supplied by the blood flow, and so the metabolic rate should be proportional to the total blood flow. Okay, and now we see here this Q0 depends, it's proportional to nk, it's proportional to nk, because the rest here are just constants which are the same for all sizes, mammals of all size. So we see the metabolic rate is proportional to the total number of capillaries. That makes of course sense here. I mean, you have the system, and we say we have the fractal thing, and we need a fractal because at every small end member of the fractal we can do some reaction. Then the metabolic rate scales with number of capillaries. Okay, that's a first nice result. And now Well, it's the first direct consequence of this. And if the metabolic rate scales with body mass to an exponent alpha, yeah, then directly we know that also the number of capillaries should scale with the body mass to power alpha. But the number of capillaries, that's Nk that we saw here, is just the branching ratio to power k. And so this, now we don't write a proportional constant, we write as an identity, then we have m divided by a constant m0 to power alpha. And then we directly get a constraint. So we see the number of branchings in the system is proportional to our scaling exponent. And then here we have a logarithmic dependence on the body mass divided by our branching factor. So directly we obtain that the critical exponent that we find in the system is proportional to the number of branchings, but this scales also with the logarithm of body mass. The total number of branches grows logarithmically with mass. And for example, if we take a whale, which is still a mammal, right? Bigger than the animal, the elephant. This has 10 to 7, is bigger than mouse, or heavier than a mouse. But here we have a logarithmic thing. This means only 70% more branchings. So these were the first consequences of all this theory. Now let's see how we can proceed. So to this equation here we came when we looked at the total flow. We were interested in total flow and blood flow through the vessel. So now in the next step we are interested in the total volume of all vessels. So let's see if we can calculate this. Total volume of the vessel system. Which means the total blood volume here. And basically this means the total blood volume gives us also the total mass of the organism. So we say we're interested in the total blood volume, and which this should be proportional to the total mass of the organism. So, and how do we get this? So we make the following calculation. So we say the total volume, now we have to sum up the number of branches we have at a certain level in the fractal times the volume of a certain vessel at level K. So Vk, so that's the, so here Vb is the total volume of the system, and Vk is the volume of a single vessel at level K. And then at every level we have K branches, so K vessels, so we have to multiply them, and then of course we have to sum, because the blood can be in the aorta or in smaller vessels, so we have to sum from the 0th until our last level. Okay, so let's see what this gives us. So we have to sum this up from K equals 0 to capital K. So now what's the volume of a vessel? That's P, the radius at level K squared, times the length K, and then this Nk equals our branching factor to power K. So now we want to rewrite this in something more simple, and in order to do this we make a trick that we say, okay, we relate this volume here at a certain depth to the volume of our smallest vessel. So let us write this here. So what is the volume of a capillary vessel? So that is equals P R capital K squared L K. So, and then what's the volume at one level smaller? So the volume at a level K minus 1, yeah. So this is a larger volume than the volume of a smaller vessel, and maybe let's first write it down. It's P R K minus 1 squared L K minus 1. And now we use these scalings here. So we have this scaling of radius is beta and scaling of length is gamma. This means this is, so the pi here, and then we have the radius K squared divided by beta squared, and then we have the length K divided by gamma, and so we see that's the volume at level K divided by gamma beta squared. So we see the volume of a vessel, yeah, at the next level is given as the volume at a deeper level in the branching divided by gamma beta squared. And now we can, if in the sum, we can now relate every term here by this formula to the size of the capillary. So that we have here this sum, K equals 0 to capital K, and now we have here this factor gamma beta squared, but we have also here this n to power K, maybe let me write it first down and then you can see that this is correct. So we have here, we take here an n also to the to this n gamma beta squared, the whole thing to power K, times, now we take the volume at level k, so p radius k squared L capital K times n to capital K. So here, so we have the total flow, the total volume in the capillary, so the volume of a single capillary times the total volume, the number of all capillaries, so that's the total volume in the capillaries. But now in a single level, so we have first to get the volume to the level k, so we have to multiply by gamma beta squared to k, and then we have to get to the number of branches at a certain depth k, and then we have also divide by n to power k. And so, but this here is a constant, yeah, and then we just have to sum up this term here. So so what we managed to do when we wanted to calculate the total volume of all vessels, so we have here a sum of all volumes, and we have written this as the product as the total volumes in the smallest, the capillary branches, divided by a factor which gives us the volume then only at a certain level, small k. And no, and this here is just our volume of a capillary. And now we can work this out. This is a geometric sum, finite geometric sum. Which we can work out. So this gives this factor n gamma beta squared to power minus k plus 1 minus 1 divided by n gamma beta squared to power minus 1 minus 1. If you remember, I mean, the geometric series, the sum of r to power k from 0 to n equals 1 minus r to n plus 1 divided by 1 minus r. That's this geometric series which I plugged in here, which gives this. So we have got rid of the sum, and then we have still volume k times nk. So we have n to power k times the volume k. And now we want to reduce this, and we make use of the fact that n gamma beta squared is smaller than 1. So this combination, the scaling factor what we have here, is smaller than 1. And now let's see how we can rewrite the whole thing. First, maybe we multiply everything by n gamma beta squared, and then we have this. So let's maybe first let's take out our vk n to power k. Then we multiply everything by n gamma beta squared, and then we have a denominator 1 minus n gamma beta squared, and then we have the rest of this here, and then we see what we have left here. only a factor k of this. We have 1 over n gamma beta squared to power k minus n gamma beta squared. And so this term we forget. If this, since this is small, this we can forget compared to this here. And now we see the n to power k, they cancel here, and the whole thing is equal to, now we have the volume of a capillary times gamma beta squared to minus k times the rest 1 over 1 minus n gamma beta squared. And this here, when you go what we had here for the volume of the capillary, that was the transition from volumes to different levels. If we revert this to the volume of the aorta, then we see this is the volume of the aorta, this factor here, times 1 over 1 minus n gamma beta squared. So there was maybe a longish calculation, but it was just summing up the volumes of all the vessels at all levels, taking into account how many vessels we have at a certain level. And now our idea was that this is proportional to the body mass, and now we see that yeah, so I mean, so in the end, so we see that this crucial term here, so the scaling factor which scales us the volume of a capillary to the volume of the aorta, this must be proportional to m, because the capillary, we said that's the end membrane, it has a volume which is totally independent of the animal. It's the same for a mouse or an elephant, and that's just our parameters of the model, which also shouldn't depend on mass. So only this term can depend on body mass. So we know that gamma beta squared to minus k should be proportional to the mass of our organism. And now we can compare to what we had before. Before we had a number for this k. Here we had this formula. Maybe we write this again, but we solve this here for alpha. If we solve this formula what we had before for alpha, so before we had alpha equals to k ln n divided by ln the logarithm of the mass. So that's just, this formulas are solved for alpha. And now for the body mass we can plug in what we had here. So we plug this in, taken together, then we see that our alpha, so that's the exponent we are interested, equals to k ln n divided, now we put in this here for the mass, so we take the logarithm minus k, then we have the logarithm of gamma beta squared the case cancel, and then we are left with our critical exponent is minus logarithm n divided by the logarithm of gamma Petrus squared. And so now suddenly we have a formula which gives us our critical exponent of our metabolic scaling in terms of our fundamental parameters, the branching ratio, the reduction in length, and the reduction in volume of vessels when we go to a different level. Now, since this video is getting too long, I will make a break. So what we need to calculate next is we need to find some rules for this gamma and beta. But we do this in the next video because it's getting too long for the moment.